It's mysterious and wondrous. Welcome to the world of relativity. We'll derive the Lorentz transformation in this video. Special relativity theory has two major postulates, the principle of relativity and the principle of the constancy of the speed of light. The principle of relativity states that physical laws are the same in all inertial reference frames. We have previously introduced inertial reference frames in an earlier video, and, based on the definition of inertial reference frames, we can deduce that the coordinate transformations between them must necessarily be linear transformations. Geometrically speaking, a linear transformation preserves the properties of lines, ensuring that straight lines remain straight and parallel lines stay parallel. Algebraically, a linear transformation can be described using simple linear equations. The principle of the constancy of the speed of light states that the speed of light in a vacuum remains constant across all inertial reference frames, specifically approximately 300,000 kilometers per second. Based on the concept of linear transformations and the principle of the constancy of the speed of light, we can derive the Lorentz transformation, which differs from the Galilean transformation and serves as the foundational mathematical framework for special relativity. The space-time coordinate system includes both spatial and temporal axes. Typically, the unit of time is seconds. For space, we use light seconds as the unit. A light second is a unit of length, defined as the distance light travels in a vacuum in 1 second, which is approximately 300,000 kilometers. With such a unit, even Earth, despite its size, becomes merely a negligible point in the coordinate system. Objects in our daily lives, even as fast as supersonic airplanes, would appear nearly vertical lines in this coordinate system. One key feature of the space-time coordinate system, defined using seconds and light seconds for time and space, is that the world line of light is a diagonal straight line with a slope of 1, indicating that it forms a 45-degree angle with both the space and time axes. Light's world line doesn't necessarily pass through the coordinate origin, but any light moving to the right will always have a world line with a slope of 1 parallel to others. Conversely, light moving to the left has a world line with a negative slope perpendicular to that of light moving to the right. In special relativity, the space-time behavior of objects approaching the speed of light significantly diverges from Newtonian physics. Thus, using a space-time coordinate system with seconds and light seconds as units proves particularly effective for visualizing Lorentz transformations and demonstrating key concepts in special relativity. In Alice's reference frame, there is a train traveling at high speed to the right, and the rear end of the train passes through the origin of the x-axis exactly when time is 0. Draw separate world lines for the front end, midpoint of the train, and rear end. Repeat the process, but this time install a spotlight at the rear end of the train. The spotlight shoots a beam of light just as it passes through the origin of the coordinates. Because the light second was chosen as the unit of spatial length, the world line for this beam of light is a straight line with a slope of 1. Repeat the process. This time, we put a spotlight at the front end of the train as well and mark the midpoint of the train. Choose the exact time to turn on the spotlight on the front end so that the light from the front end and the rear end reach the midpoint of the train just at the same time. Let's see what we get in Alice's space-time coordinate system. First, there are 3 world lines for the front end, midpoint, and rear end of the train. The equation of the world line for the rear end is x equals the speed of the train, v times t. The other 2 world lines are parallel to it. There are also 3 events that occur in space-time. Event A is the spotlight at the rear end turning on. Event B is the spotlight at the front end turning on. And event C is the midpoint receiving lights from the front end and rear end at the same time. Next, we come to Bob's world. Bob is the one sitting at the rear end of the train. Let's analyze how he feels about these world lines and events. First, Bob is sitting in the train. The train is stationary from his perspective. The world line for the rear end will always have spatial coordinates equal to 0 in Bob's reference frame. Therefore, the world line for the rear end will be the time axis of Bob's reference frame. Next, let's analyze when events A, B, and C occur in Bob's reference frame. For a stationary train, to reach the midpoint simultaneously, light must be emitted from both the front and rear ends at the same time. Event A and Event B are events of turn on the spotlights at the front end and rear end of the train, respectively. Therefore, they must occur simultaneously in Bob's frame of reference. The time coordinate of Event A in Bob's reference frame is 0, so the time coordinate of Event B in Bob's frame is also 0. In Bob's reference frame, the point with time coordinate 0 is a straight line, which, according to the properties of linear transformations, must also be a straight line in Alice's frame, that is, a straight line passing through points A and B. Each point on this line has 0 time coordinates in Bob's reference frame, so this line will be the x-axis of Bob's reference frame. We have found the locations of Bob's reference frame's time and spatial axes in Alice's reference frame. If we analyze further, we can find that the angle between the time axes of both reference frames is the same as the angle between their spatial axes. The proof is simple. Extend line BC until it intersects the world line of the rear end at point D. Line segments BC and CD are divided by 3 equally spaced parallel lines, so the lengths of BC and CD must be equal. And the 2 white world lines, which are world lines of light traveling in opposite directions, are necessarily perpendicular. Therefore, we conclude that triangle ACD and triangle ACB are congruent. Since AC bisects the angle between the time axis and the spatial x-axis, the angle between Alice's time axis and Bob's time axis is necessarily equal to the angle between Alice's x-axis and Bob's x-axis. We have found the location of the time and space axes of Bob's reference frame in Alice's frame. The Lorentz transformation, by necessity, transforms these 2 lines into vertical and horizontal directions, respectively. Now let's visualize the Lorentz transformation and explore how world lines and events are positioned differently in the spatial and temporal dimensions within Alice's and Bob's reference frames. The above is a visual derivation and demonstration of the Lorentz transformation, lacking a quantitative expression. In the upcoming video, we will derive the Lorentz transformation formula through rigorous algebraic methods. This is the standard form of a linear transformation in mathematics. Here, L is a 2x2 matrix and B is a 2-dimensional vector. Break this standard linear transformation into 2 parts. The first part represents a translation of the coordinate axis, which is a very trivial change in physics that we do not concern ourselves with. We are only interested in the linear coordinate transformation between 2 reference frames that share the same origin, which is the second part. The Lorentz transformation is a linear transformation and also fits this form. For convenience, we refer to the reference frame in which t and x are located as Alice's reference frame. The reference frame in which t' and x' are located as Bob's reference frame. Bob moves at a velocity v relative to Alice. Since the transformation differs at different velocities, L will be a function of the velocity v. Our goal is to obtain the specific expression for the Lorentz transformation matrix L. Based on the required physical properties of the Lorentz transformation, we can enumerate the conditions that L must fulfill. First is the principle of the constancy of the speed of light. Change the coordinate values in Alice's reference frame to satisfy the equation of motion for light emitted from the origin. That is, the x value equals the speed of light times t. Similarly, in Bob's reference frame, the same light must also satisfy the x' equals the speed of light times t'. If we use seconds as the unit of time and light seconds as the unit of distance, then the speed of light c is 1, and the distance traveled by light will be equal to the time. By performing some simple derivations, we can obtain the conditions that the Lorentz transformation matrix L must satisfy due to the principle of the constancy of the speed of light. Let's look at the second physical condition that the Lorentz transformation must satisfy. Bob moves to the right at velocity v in Alice's reference frame. Bob's trajectory in Alice's reference frame satisfies the condition that the distance equals the velocity times t, while Bob's trajectory in Bob's reference frame keeps the spatial coordinate at 0. Also, through simple derivations, we can obtain the second condition that the Lorentz transformation matrix L must satisfy. The third physical condition can be obtained from the inverse transformation. Bob moves at velocity v relative to Alice, which means Alice moves at velocity minus v relative to Bob. The same Lorentz transformation, with v replaced by minus v, must convert Bob's coordinate values back to Alice's coordinate values. This means that L of v multiplied by L of minus v results in the identity matrix. The fourth condition can be obtained from the left-right mirror symmetry of space. If we reverse the spatial coordinates of both reference frames, similar to swapping the left and right sides of space, x will become minus and the velocity v will become minus. The entire transformation still holds. From this, we can derive the condition that the transformation matrix L must satisfy. Actually, these physical conditions, except for the first one, are also satisfied in Newton's world. You can verify this yourself using the Galilean transformation. Based on these conditions, although it is somewhat tedious, using only high school mathematics, we can derive the specific form of the Lorentz transformation matrix. If we do not use light seconds as the unit of space, the form of the Lorentz transformation will become a bit more complex. The Lorentz transformation, which blends time and space, is a fundamental aspect of special relativity. But what does this mixing represent physically? How should we conceptualize time and space? These are the questions we will delve into next.